This is Sound, Noise, Acoustics, Engineering Podcast, episode number 3. Brought to you by Sound Solutions, an independent acoustical consulting firm at ssacoustical.com. We provide you with knowledge and resources to address acoustical issues. I'm Bill Holliday. Thank you for joining me on this episode. I'm going to talk about road noise projects. Anytime a road is expanded, moved, modified, or a new one is built, and there's residences or schools or churches, we're going to call those noise-sensitive receivers nearby, a noise impact study has to be conducted in the U.S. The study looks to see if noise mitigation, like sound walls, are needed or justified, and if they're going to need to provide them as part of the project. So sound walls are the primary noise reduction measure. In some areas, you can count a reduction from rubberized asphalt concrete. So it's asphalt that they put on that's rubberized, and it helps reduce that wheel-road interaction noise. You can also move the road up or down, or in some cases move it away from the receivers. That's usually not too practical or doesn't provide much reduction. And in some cases we've seen, if it's not feasible to buy the property, for the project to buy the property, or mitigation to go in, sometimes we've seen where they improve the windows, improve the exteriors of the homes. And that's usually windows, door seals, providing air conditioning so that windows can be left closed, something like that. However, sound walls are by and far the most practical, most common option you'll see out there. And usually you'll see them just these big concrete tilt-up panels. And that's for durability, but you don't have to use concrete. If you can block that line of sight and the material, the noise going through the wall is 10 dB less than the amount that's diffracting over, you can use wood, you can use a berm, of course, you could use rock wall, you could use loaded vinyl, but it doesn't have to be concrete. Plants don't do much. They're psychologically helpful if they block the visual piece, but having a row of trees, acoustically, single rows, unless they get very thick, multiple rows, 100 feet deep, pretty hefty vegetation, you're mostly just providing visual and not acoustical attenuation. So when you do these road noise studies, you start by just evaluating the site. Where are these receivers, these noise-sensitive properties? And they could be, again, libraries, hospitals, churches, parks, schools, homes. And identifying representative ones. You don't have to necessarily hit every single one. If there's a group and there's one that's closest and you evaluate there and there's no issues, well, then if there's no difference between them except for distance from the road, the traffic volume's the same, everything else is the same, then you're not productive picking another site in that group that's further back. So you're looking for representative locations, worst case locations. Now, if that closest one does have an issue, well, you're going to have to evaluate the next ones further back to see how far that issue goes, how many people are impacted, and what's the extent of that impact. And when we get into mitigation, you'll need more locations to see how many people are being benefited by the mitigation. But initially, you're looking at representative noise-sensitive properties or homes. And so once you've established what this site's going to be, what the general layout is, you predict the existing noise levels from that existing road at representative noise-sensitive receivers. And it has to be at the loudest hour. And so we look at usually rush hour, morning or afternoon. Sometimes it's not rush hour, but a traffic engineer, someone will provide you with data saying here's peak hour noise, and you're going to plug that in and predict what the existing noise is. And right now we use this free software from FHWA, Federal Highway Administration, called TNM, or Traffic Noise Model. And I'll go over what that looks at in a second, but you plug the information in there and you predict the existing noise. Then you go out and measure during the rush hour, the loudest hour, and you make sure that model's correct. It has a lot of variables like ground type and temperature and humidity and things that, well, you might have to tweak a little to make sure you're getting the right predictions. And you'll do traffic counts while you're measuring so that you're measuring apples with apples. Then you go out and you predict, you don't go out, you sit at home or at the computer, and you predict the future case loudest hour conditions using this TNM software. And you compare, all right, what's that future noise level versus the criteria? And then what's the change from the existing with those traffic engineer numbers with the future? And what is that change, and see if there's an issue there. And then if you're above the limits, then you have to look at mitigation. You have to look at attenuating the noise or reducing the noise somehow. And again, barriers are the most common solution. In some cases, again, you can get some credit for the rubberized asphalt. So regulations, let me just jump into that for a second. First, you need to determine who's funding the road change. And usually the engineering firm that you're probably working with will tell you. But if it's federally funded, they have a set of rules. If it's state funded, there's a set of rules. If it's a county or city project, they have different guidelines. And they're all going to be pretty similar. Most everything I've seen follows this FHWA, Federal Highway Administration, noise abatement criteria, or this basic guideline. And what FHWA says, hey, for these residences, churches, parks, hospitals, schools, the noise sensitive spaces, you're limited to approaching 67 dB. That's kind of funny. The approaching, to approaching it. So for a federal project, they're saying, all right, well, 1 dB is approaching, so you got to be 66 or less, or you have a problem. And that's for the future noise level. And that's looking at the 1 hour average noise level during peak rush hour, peak traffic hour. And there's a second criteria, and they say, hey, the change between existing and future, you can't increase by more than 5 to 15 dB, depending on where we are. But let's say 15 dB. So you can't make a 3 times the noise level or perceived noise level change without looking at abatement. And usually we don't see that big of a change unless it's a new road going in and there's nothing there currently and you're throwing a new road in, and then you could see some large changes. But each state, county, city, they're going to tweak that definition. They're going to have a different definition of what approach means. They're going to have a different definition of what that allowable increase is. So in Arizona, where I am, ADOT says that limit is 64 dBA. If you go above 64, you got to look at mitigation. And then the state also says, hey, that rubberized asphalt concrete, you can't count it. Throw that out. You can't use it. Don't use that as mitigation. Now, the county where I'm in, they say 66 is the limit. So above 66, you got to look at mitigation. If it's below, don't look at it. And they say, if you put on rubberized asphalt, we're giving you a 3 dB credit. So really, you could be at 69, throw on rubberized asphalt, be at 66, and you're in good shape. So we're looking at 69 to 64 between the state and the county, 5 dB difference in the regulation. Then both of them say a substantial increase. That difference, 15 dB is the rule for that second part of the rule. 15, if it's above a 15 dB change, look at mitigation. If it's below, don't worry about mitigation. So you need to know whose guidelines you're following and make sure you understand those. I've tested this rubberized asphalt concrete as an aside, and it really does great for that wheel road interaction. It does nothing for engine noise, obviously. I mean, I guess it could for reflections, but mostly we're really dealing with wheel road interaction that it takes care of. So if it's a flat road or downhill or mostly cars that have a lot of wheel road, not as much engine noise, it's great. We saw big reductions, 6, 7, 8 dB reduction. If it's on an incline or you have lots of trucks or motorcycles or big engine noise, you're going to get less. And then over time, it can wear. It has to be patched with rubberized asphalt concrete patching. And so it's going to have some issues. Of course, weather, if it's rainy or certain weather conditions are going to affect the effectiveness of it. But in general, we've seen it do good performance, but the state says, hey, you can't touch it. We're not going to allow it. And again, there is variations depending on what the mix of traffic is, what the inclines are or aren't. So once you know so you run this analysis and then you know, all right, which residences are above the limits. Then you got to look at mitigation. You need to look at it. So you talk to the engineers about moving the road. You can talk to them about speed controls or some other controls. But generally, if there's an issue, we're looking at barriers. And then each jurisdiction is going to have different rules. So the county I'm in says you can't do barriers over 10 feet high. The state says they can't be over 20 feet high. Let's see, if it's only one noise sensitive property that's being helped by the barrier, some regulations will say, no, that's not reasonable. So we're looking for feasible and reasonableness. And so even if they're in violation, or even if the noise levels are above the limits and it's only one person being affected, they can't get helped. And so you calculate. So let's say there's going to be different cost limits for these barriers. So you look at the impacted receivers and you calculate what size of a barrier do I need to provide a significant reduction. And usually a benefited receiver is defined as having a 5 dB reduction from the barrier. So how big does that barrier have to be? Figure out the square footage, and then there's going to be a cost in the state or the county or the city regulation. For Arizona currently, and this changes, but it's $35 a square foot. So we can figure out, all right, how much is that barrier going to cost? And then you have to determine how many people are being helped, how many are getting this 5 dB reduction. And you play around with the size to benefit as many as you can. And then there's going to be a limit there. So we have a $49,000 per benefited receiver is the limit. So you divide the total cost by the number of receivers, and you see if it meets that. If it doesn't, well, they're out of luck. I mean, you can play with different sizes, do the best you can, but if it's $200,000 per benefited receiver, it doesn't meet the guideline, and they don't get a barrier. Benefited receivers are generally ones that get at least 5 dB reduction. There's some regulations, like Arizona here, that says you got to have some of them, a percentage of them, getting 7 dB noise reduction. They're only dealing with mitigation for the first floor. So if you have a high-rise, which we don't really deal with too many in Arizona, but if you do have multi-floors, we're only looking at first floor, 5 feet above the ground. And then they do say, if there's a split, like driveway splits, you're probably not getting anything. That's usually not in the regulation, but if you calculate it, you'll find, I guess that's a rule of thumb I'll go over, but breaks in the barrier really hurt the effectiveness. If the barrier, and no mitigation for undeveloped properties unless they have some building permit before they call them the EMER documents, but you can't have the road, ready to go, and then some undeveloped property is getting developed, and then they're requesting barriers. Too late, analysis is done, you don't get a barrier. So if the barrier is determined to be feasible and reasonable, then you also have to get a majority of those impacted properties to approve it. So we've had cases where the noise levels are too high, we evaluate barriers, they get a barrier, and then they don't want it because they don't want to block their view or whatever the reason is. That's fine, they don't have to have it. And then with these traffic predictions, let me just touch on this for a minute, because this is valuable, I think, for, well, some of this for other barrier analysis. But here's a few rules of thumb. So if you double the traffic volume, you get about a 3 dB increase. You need to increase that volume a lot to get a big increase just from volume. If you double the distance from the road, you get about a 3 dB reduction. And there's atmospheric reduction and other factors. So it's not perfect calculation, but if you go from 100 feet to 200 feet, you're dropping about 3 dB. If you go from 100 feet down to, if you go from 200 to 400, drop another 3 dB. 400 to 800, drop another 3 dB. And there's an easy calculation, 10 log of the initial, well, of the future distance over that initial distance, and you can get a, how much of a difference that's going to make. But, and I'll put that on the web. But that's a good kind of rule of thumb. If you block the line of sight between the noise source, the vehicles, and that's the wheel, road, and the motor, and so autos are going to be a lower noise source height, and trucks will be a higher noise source height. But if you block it between that noise source and a person's ear, your receiver, you'd probably get about 5 dB reduction if you just barely are breaking it. And then every foot you go up, you'll be reducing it more. Big rule of thumb. That's not it could come out different than that. Barriers are most effective close to the source or close to the receiver. Right in the middle of the least effective. And let me see, if you completely block half the road, so you have your barrier, you wipe out half the road, you get about a 3 dB reduction. And that kind of ties in with doubling the traffic. And usually breaks in the barrier, I guess I mentioned this before, render that wall ineffective, or not ineffective, but it won't give you the 5 dB reduction you need for it to count as a good mitigation or a feasible and reasonable mitigation measure. So this TNM program, it takes into account the road geometry. You plug in the coordinates, the X, Y, and Z coordinates of the road. You put in vehicle speeds, the vehicle volume, the mix of traffic, the topography, the ground types, and the location of the receivers. And then it churns out a number. Again, you verify that number with the existing based on your counts as you're sitting there counting vehicles, types of vehicles, and you are doing your measurements. You want to calibrate it so it's going to be pretty reasonable, pretty close to what you're measuring. And then you plug in future numbers, future volumes, future configuration, and you come up with new numbers. It's not perfect, but it's pretty reasonable. It's what we use. So whether it's perfect or not, that's how we determine if you get walls. It's what's being used. All right, I think I've taken up enough time here. This wraps up episode 3. Next podcast, I'm going to talk about room acoustics, and I'll talk about a banquet hall, kind of reverberation time. Thank you very much for listening to Sound, Noise, Acoustics, Engineering Podcast. I provide you with knowledge and resources to address acoustical issues. I'm Bill Holliday with Sound Solutions, Acoustical Consulting at ssacoustical.com. As always, I appreciate any feedback you have. You can go to the website, and there's a bunch of ways to link or to contact. My email is bill@ssacoustical.com. I'm also have a Facebook. Sound Solutions has Facebook that I'll probably get it if you put a message there. All right, thanks a lot.